Hey guys, welcome back. This is part 3 of chapter 9, which is the thermochemistry portion of this unit. This is Dr. Rhonda Kofelt. Glad to have you with me today. The problems that we're going to be working in this, we're going to talk about things, of course, but we're going to calculate the enthalpy, the change in enthalpy of formation using standard enthalpies of formation, and we're going to discuss what that means, okay? So standard states, we've seen these already, standard conditions, you know, whether you're talking about gases or whatever. If it's a gas, it's pure gas, it's going to be 1 atmosphere of pressure. A pure solid or liquid, it's going to be its most stable form at 1 atmosphere. And then whatever temperature you're doing, usually it's room temperature. And anything that's in solution should be in 1 molar. So that's the standard conditions when you're looking at energy type changes. The standard enthalpy change, okay, is going to have that little 0, right? Remember that? That means it's at standard conditions. So when you look that up, there's going to be a table and it's going to have standard enthalpies. This is the enthalpy change when all reactants and products are in their standard states, okay? The standard enthalpy of formation, okay, that's what has the little F on there, excuse me, is the enthalpy change for the reaction forming 1 mole of a pure compound from its elemental constituents, okay? The elements must be in their standard state, that is, their most stable form at room temperature at 1 atmosphere of pressure. The delta HF0 for a pure element in its standard state is 0 kilojoules per mole. So here are some of these standard enthalpies of formation. And this is at 298 K, which is 25 degrees C. And so you see they're all over the place. Notice, though, the ones that have zeros. Chlorine it exists as a gas in nature as Cl2. So that's why it's a 0 in its elemental form. Calcium, metal, is a 0, carbon is a 0, etc. So whenever you see one that's in its elemental state, don't forget about those diatomic gases. So when I said we're forming something from its elemental components, okay, its elements. So if you're forming magnesium carbonate, then you're going to add magnesium solid, which is its normal state, plus carbon, plus oxygen, and that's going to give you the magnesium carbonate. If you have C6H12O6, you're going to make that from carbon, hydrogen, and oxygen in their elemental states. And when you do that, there is a delta H of formation associated with making those. And that's what you saw on the charts. Okay, so standard formation is from the elemental constituents, magnesium, carbon, and oxygen, which makes magnesium carbonate. All right, so if it asks you for the equations for the formation, you've got to use those elemental forms. And then I'm giving you one to try out. So any reaction can be written as the sum of its formation reactions, or the reverse of the formation reactions, just like we saw in Hess's law. All right, but in this way of calculating the delta H0 for the reaction, it's going to be the sum of those. And so if you recall, we've always, whenever we do this, it's going to be products minus reactants, okay, the sum of all of the delta HF0 of the products minus the sum of all the delta HF0 of the reactants. And so this is where you see this mostly used. So the enthalpy change for combustion of methane, for example, of course, has 3 steps, okay? And so it has 3 steps and each of those has an associated amount of heat that goes with it. All right, usually you see these, if you look them up, they're written as negative numbers because they're doing the exothermic form. But if you have to turn it around, if you have to flip it, just like we did with Hess's law, then you have to change that sign. All right, so let me show you what I mean. All right, so I'm going to use the standard enthalpies of formation to determine the standard enthalpy of the reaction. So when I'm given these, it's going to be the products minus the reactants. And then I just do the sum of all of them, and it's extensive. So honestly, what I do when I get this is I take these numbers right here and I write them underneath. Minus 45.9. Notice oxygen is a 0. NO is a positive 91.3. And water is a negative 241.8. And I do that because that way when I go to do products minus reactants, I don't get them confused. So the delta H 0 of the reaction is going to be the sum of all of the products raised to the coefficient, minus the reactants raised to their coefficient. Okay? All right, simple, simple, simple. Okay, you're going to love these. All right, so we go to the product. Our product is NO and H2O. I've got 4 NOs. All right, so I've got 4 times a positive 91.3 plus 6 times a negative 241.8 kilojoules. I should probably write what I'm doing, but you can see what I'm doing, right? That's your NO, that's your H2O products, minus the reactants, which is going to be 4 times 45.9 plus 0. All right, so it was 4 times your NO plus 6 times your water minus 4 times your NH3 plus 5 times your O2. Just want to make sure you know where they came from. All right. So then I do 4 times positive 91.3. That turns out to be, whoops. 1085. Oh, wait, I did them all together. Sorry. So when I do these together and add them, I'm going to get a negative 1085.6, and these are all kilojoules, right? Now, the reason it's just kilojoules at this point is because this is kilojoules per mole, and this is 4 moles. So your moles cancel. So 6 moles and that many kilojoules per mole, and moles and kilojoules per mole. Just in case you're wondering where that whole thing went, because your units are actually kilojoules per mole. So that's a negative 1085.6 minus a negative 183.6 kilojoules. And you've got to make sure that you're watching these signs, because that's where you'll mess up. When I did the product of that, or I added these together after doing products, it was a negative number, then it was minus another negative number, okay? And so when I do that, of course, minus a negative is the same thing as doing plus. So it was minus 1085.6 kilojoules plus 183.6. And so that's going to give us a negative 902.0 kilojoules, and that is the delta H of the reaction by using all of the standard enthalpies of formation. So those are pretty easy. You're going to do this. The reason I go ahead and introduce this now is because we're going to do this for a whole bunch of things. All right, so you need to get a really good handle on these techniques that we're doing in this chapter, because you're going to do them with entropy and you're going to do them with Gibbs, and so it's the same exact thing. And so if you'll get this nailed down in chapter 9, it'll be super easy for you when we get to chapter 18. Your practice is the thermite reaction. If you've never seen this, it's way cool. But it's you put powdered aluminum and iron 3 oxide together, and it does this really bright light as it's burning. Okay, so I'm going to look at another one. Okay, standard the delta H0 reaction. And again, I'm gonna put these. This one just has a little kick to it because once I find out the amount of energy, then it's asking me to do something else. So I'm gonna kind of analyze what it's given me first. Okay, it says a city of 100,000 people use 1 times 10 to the 11 kilojoules of energy per day. Suppose all the city's energy comes from the combustion of octane to form gaseous water and gaseous carbon dioxide. Use standard enthalpies of formation to calculate the delta H0 of the reaction for the combustion of octane. Okay, that's part A. And then determine how many kilograms of octane are necessary to provide this amount of energy. All right, so the first thing we want to do is that delta H0 of reaction. And I know how to do that. And so I'm going to go ahead and do like I said before. I'm going to write my little numbers down here so it keeps me honest. Minus 250.1, and these are all kilojoules per mole. Oxygen's always 0. Minus 393.5 for CO2, and minus 241.8 for gaseous water. Steam, as we say in the business, right? Okay, so now I'm going to do the sum of all, because the delta H0 of the reaction, sum of all of the products minus the reactants. All right, and so and so we are multiplying them by their coefficients, so it's going to be equal to our products, which are the minus 393.5 kilojoules, and that's, how many do I have there? I have 8 moles. Remember how that goes away? Moles times kilojoules per mole, plus 9 times a negative 241.8 kilojoules. All right, that was my products, and then minus my reactants, 1 times a negative 250.1 plus 25 over 2 times 0, 0. All right, and so when I do the products, I'm going to get a negative 5324.2 kilojoules minus a negative 250.1 kilojoules. And so that's going to give me a negative 5074.1 kilojoules. And I'm just leaving those figures there, so don't get all excited on me. All right, just so you can see how close you were with the way I was calculating and before I'm rounding. All right, because I like a lot of times not to round until I get done, right? All right, so that is the delta H0 of that reaction. So delta H0 of the reaction is going to be a negative 5074.1 kilojoules. All right, but the other part it asked me was how many kilograms of octane are going to be necessary to produce that 1.0 times 10 to the 11 kilojoules. All right, so I know what? I know that this right here is per mole of C8H18. Okay, that's what delta H0 of the reaction is. It's kilojoules, and because it was based on 1 mole of that octane. So this turns into a dimensional analysis at the end. I've got 1 times 10 to the 11 kilojoules that I want to make times 1 mole over a negative 5074.1 kilojoules, right? Because that's how many per mole of C8H18 times, and then it wants kilograms, okay, so I can get it to grams and then get it to kilograms. So if you look up C8 and H18, that's 18, and 8 times 12 is what, 96, I think. All right, it comes out to about 114.22 if you use all the decimal places. So 114.22 grams of C8H18. And Lord, if you've forgotten how to do this, go back and remind yourself how to calculate the mass, molar mass, okay? And that's in 1 mole. So how many grams is in 1 mole of C8H18 times, got to get rid of grams because I want kilograms, so there's 1 kilogram because it's big, in 1,000 grams. All right, so let's see where I am. Kilojoules, moles, grams, kilograms. Okay, so I should be good. So when I put all that in my calculator, being very careful, I get 2.3 times 10 to the 6 kilograms, not kilojoules, of C8H18. So it would take 2.3 times 10 to the 6 kilograms of octane to supply the energy for a city of 100,000 people for 1 day. That's a lot. Okay? So it just had that little at the end that, you know, once you got to this point, you had solved the problem like we did before. This is, though, how you then apply it to a real world scenario and then go back. So you can always fall back on your dimensional analysis for things like this. And you have practice. And that will be it for part 3.